Hello everybody to Sustainable River Basin Management Module 1 Part 2. We have been talking about sustainability and why it does matter, looking at social and economic aspects in our previous class, and now we will be looking at physical and environmental aspects. One of the most important reasons why sustainability matters from a physical aspect is resource depletion and pollution. We have to keep in mind the use of finite resources, and most of our resources are finite on this planet. And we can describe the process of resource depletion by referring back to Hubbert, who produced in 1956 the so-called oil peak theory, which he was hypothesizing that oil extraction could be described by a bell-shaped curve, just like the graph that is shown here. I don't want to go into the debate of his projections and the hypotheses which he came up at that time about oil peak and oil reserves. However, the process as such of resource use and consequently resource depletion are valid not only for oil, the oil industry, but also for any other resource, a natural resource. And the general process is that there is a cycle of discovery taking place. Reserves are discovered, technologies are developed, and those resources are developed. They go under production, they will be extracted, and there will be a market for it. At some point, those resources will be depleted. There might be an ultimate recovery by finding additional reserves or by developing better technologies which allow additional resource extraction. But eventually we'll come to a point which we would call end of life of such reserves, of such deposits, where those natural resources will be completely used and not available anymore out of the cycle here. So this is what applies not just to oil, but to any of the resources that we can pick, we can think of. Now let's look at some examples, and I've chosen oil and gas and phosphorus because they are key in our economy and key for our current survival as well. Let's look at the example of the finite resources use cycle that I just explained in a generic way in the case of oil and gas liquids. This is a scenario that was developed in 2004 out of industry data. What we can see is it covers a time span from 1930 to 2050. Again, we are at our magic year that we mentioned in our previous lecture already. And we have here on this axis billion barrels per year production numbers. And what you can see is that oil extraction as such started to develop around the 1930s, and it started basically on one continent in one country, and it developed in a very modest, very almost linear way and peaked, and then from this peak decreased at a very early stage in the 1970s. At the same time, we can see a shift to other continents, other countries, other regions where oil reserves were discovered, and at some point a boom started where all these reserves were taken into production, extraction started, and this point is critical to our entire economy. This is where technologies became available to drill deep holes and to access those deep oil and gas deposits, and our economy became adjusted to the availability of these hydrocarbons. We can see that those developments took place at more or less the same point in time and peaked also about more or less at the same time. There was a few slight shifts in it, but we can see that around 2010 most of these sites or areas under production saw a depletion, a resource depletion, and a reduced production of oil. And then the response to this was that another shift took place to new technologies, the so-called natural gas liquids. The top layer here on this graph, it's a very expensive technology which became available and in some of the countries also accepted and provided another way out of the resource depletion that was noticeable at this point already. And we also see a shift to more expensive or unexplored terrain, such as the polar region, the deep waters, international waters, which require new expensive technologies, but also new laws and regulations and agreements to become areas used for economic endeavors. So this is a typical image, and we can use any other mineral again to demonstrate it. So we see a shift in general to different regions, and we see also a technology development attached to the accelerated abstraction amounts over time. And then we see a dip in our exploration numbers. Let's keep this beginning of the acceleration in mind, because that is a very critical point that produced a change in our living quality, in our overall living conditions. Population numbers increased at that point. Technologies became or new substances became available based on our hydrocarbon industry, based on our petrochemistry. So it's a very remarkable point which we will refer back to at a later stage. So keep this in mind. Now let's look at the so-called peak resource. I've used the term peak oil earlier. What is meant by peak oil or peak phosphorus, peak resources? It's actually the point in time at which the maximum global mineral production, that specific mineral production rate is reached. This does not mean that the resource has been exhausted at that point. It's simply that maximum production rate has been reached, and at that point less of that resource will be available, and eventually it will be exhausted. So that is a point that can shift as information and more knowledge on our resources is gained, as mapping is going on, geological exploration is going on. But eventually we will know all our resources on our planet, and eventually we will get to a point where the resources will be entirely exhausted. So let's look at peak phosphorus here. Phosphorus is quite important to the biological cycles. We humans consume about 3 million tons of phosphorus annually, and for that about 5 times the amount of phosphorus has to be produced, has to be mined. So means you see already here that there's a huge difference between what has been produced and what is extracted from a reserve or a deposit and what eventually is being consumed. That is typical, and I just want to highlight it here. That's typical for resource abstraction, that there's a large amount being lost on the production pathway. So phosphorus is vital for plant growth, and for that reason it is vital for food security. Let's look at this aspect of food security. We have here phosphorus production in million tons per year, and here we have our time scale starting from the 1800s to about today. And we see that at some point most of the phosphorus sources were either guano or manure, and human, very small, minor amount human excreta. And then there's a technology shift taking place where phosphate rock was started to be mined and converted into fertilizers, which were then used or are used to improve soil quality, and in that way produce more food per hectare. So this huge amount of phosphorus which became available through mining phosphate rock allowed, among other factors which we will come back later, the so-called Green Revolution, and it actually allowed countries like India to become self-sufficient and to produce all the food required to feed the entire population. So this goes hand in hand, as you can see again, with the magic year of around the 1950s, when also oil production became accessible due to the technologies available. Now, what we have to mention and keep in mind here is that phosphorus is scarce and finite again, and right now we don't have alternative means next to mining to replace or substitute our fertilizers. We can only fall back onto our manure or to other sources, which we will be mentioning at a later stage when we talk about nutrient cycles. So this is the example of phosphorus. Just summarizing the projections for phosphorus, we have here % of maximum production. So around 2000, we had industries and scientists believe that we have reached our peak phosphorus production, and that from this point onwards, the amount of phosphorus that can be extracted is decreasing, and in about 50 years, or around 2050 again, we will reach about 50% of our initial maximum production. There are different scenarios again, which have to be seen in the context of the projection for population growth. You remember that population growth is in one of the scenarios is expected to decrease in the year of 2050, and this is also when the fertilizer production will see a reduction. This is to mention also that 2050 is not a year which is far away from ourselves. It is something that we will face, or many of us will face this decrease or this major tipping point in resource availability, in living quality, and in population decrease of population numbers. So that is something we have to face, and it's not even something for the next generations to look at. Now, what does mining mean? Just as example, phosphate mineral mining means essentially digging a hole and extracting the mineral resource from an open pit or from underground mines. It usually would look like this. It affects water bodies, and it affects soil and soil fertility and land use in general. So this is going hand in hand with the depletion of the resource. So there's a degradation of our land and water quality or air quality attached to this. Now let's look at current economic models, because there must be a reason for why those processes are like this. And we look at economic growth and consumption. And we'll question whether our current economic models are actually in line with the sustainability concept. So what we are doing right now is that we are using natural resources, or also we can call it natural assets. We extract them from the environment, we use them straight, or we have to convert them into some other materials or in fuels, and then we will use them, we will produce waste and return those into the environment. So it is essentially a straight line from a source somewhere to a sink somewhere else. And our economies are building on, our economic model is building on growth, means that we need larger sources. The source has to increase, and at the same time, obviously, the amount of waste will increase, so we need more space, more volume to deposit our waste somewhere. The sink has to be available. So summing this up, we have an economic model that is linear right now, and it is based on economic growth and consumption. If one of the two fails, then we will have an economic crisis. Now, looking at the term natural capital and natural assets, what is it? What we mean by natural capital, natural assets, essentially clean air, water, we will focus on water later, soils, minerals, ore, plants, animals, and you may find other items that you can also categorize as natural assets. So if you look at it from an economic perspective, the natural resources are essentially inputs together with environmental services for an economic production and output. So, and our natural capital is composed or can be distinguished into renewable resources, non-renewable resources, but in either way, both can be considered as finite. Why are renewable resources to be considered finite? This is because quality decreases as we use those resources, and they may not reproduce as fast as we need them, or they may be polluted in such a way that they become non-usable for us. We will stop at this point and continue with part 3. next time.